So we are now on chapter 4. We are going to discuss circular motion. And in the previous chapter, we've studied motion in which situations where we determined horizontal motion. We determined whether the object is moving at a constant velocity or changing its velocity, therefore it's accelerating. And we also determine the forces that involved in that. We find the magnitude, we find equations to solve that. So in this chapter, we'll focus on circular motion. This is a very simple type of motion in which we look at the sum of the forces, the acceleration of the system, and we also will see that this will continually change. One of the most common question in here is, can the object that is moving a circular motion, which you understood that in our warm-up activity, that an object will move at a constant speed. However, if it's in a circular motion, does it changes its velocity? So what is our answer on that? Is it a yes, it's accelerating, or is it a no, it's not accelerating because it's moving at a constant speed, therefore there is no change? Now, it's different. For linear motion, we would say it's moving at a constant velocity, doing horizontal motion. There is no acceleration. But for circular motion, we would take note that the object moving in a circle continually changes its direction. Therefore, it is accelerating. So we're going to find that out. We're going to explore what causes it to change. So yes, the answer, because the object is changing direction. And we would notice that if you're riding the merry-go-round in here, you would notice that the object may have a constant speed all throughout, but then its direction changes relative to the frame of reference. So the same thing with this manual washer, where it continually changes the direction of the clothes inside, but it does move at a constant speed. And that's what we call a uniform circular motion. And that is what we're going to deal with in terms of our concept today. So let's say, for example, the object moved initially at this point, and then for some time it moves in a circular path at this point. So we could say that its direction have changed. So we could take note that if the direction of change, therefore there's a change in velocity. That gives us the idea of the change or initial. So we could use that as initial. If it is changing velocity, does it accelerate? So that's another question. So most of you probably will figure that out, but if we try to draw a component of these two, so let's say I will have the V1 in this direction. That's the initial. And I'll connect them tail to tail. So I will have in this direction. Okay. So that's going to be the direction of the final. And I would draw the resultant velocity or the speed. So you notice that this points, and that's the change. That's the change. That points towards where? It points towards a fixed point in the center. So given that, we would know that this also gives us an idea that the object is accelerating. Because a change in velocity over a certain time, it will spend some time to travel, therefore it's accelerating. So as you can see here, the velocities move around the circle, and as the velocity gets closer, we will see that the acceleration points towards the center. So we know the object is accelerating, but the question is, what causes it to accelerate? So there must be something else. And what is that? That is the net force. So there is a force that will cause it to accelerate, or refer it as net force. That causes the object to undergo acceleration, which points towards the center, because the force applied will give the direction of the acceleration, and that gives us an idea that it points towards there. And that force is called centrifugal force, the force that draws it to move towards the center. So in your homework number 16, it talks about your friend who's telling that, hey, is this possible that there's a force that pulls that out towards since there's a centrifugal force? The answer to that question is no. That's a fictitious type of force called centrifugal force. It doesn't exist. You've seen that in your warm-up, that it is something that doesn't exist. Now let's look at some properties in terms of objects moving circular paths. So we know that it is moving at a constant speed, but therefore it also changes its direction, therefore it's accelerating. Okay, but how is it related to each other? So if we have a path here, a circular path, and then if we will try to find out the acceleration, we'll get the change in velocity over change in time. So what happens if I double the velocity? So if I could double the velocity here, so 2, I know that if I double the velocity, the time it takes to move from one point to another reduces it to 1/2. Therefore, my acceleration becomes 4-fold. The acceleration equals to 4 times the velocity, which is over time. Now if I say I'm gonna triple the velocity, therefore it's gonna be 3 times shorter than the previous, then I will have over the change in time. So in this case, we'll see a pattern. So what pattern do we see? We see a pattern in which acceleration is directly proportional to the square of the velocity. So another concept that we're going to look is how does acceleration depend on the curve path, which is the radius. So in this case, what happens if we double the radius? What happens to the acceleration? So it is reduced to half of it. And then what happens if we triple the radius, then it's also going to reduce it into a third. So in this case, we'll see a relationship between the radius and the acceleration, which is inversely proportional. So from that sense, we can develop our equation for most objects that travel in circular path, which is equal to, this represents radial acceleration, is equal to the square of the velocity over the radius, which gives us a unit of meter per second squared. And that's it for this section.